Lesson 4, we introduced polymorphic functions. Remember that polymorphic functions are functions that behave differently based on the number of input arguments or output arguments that they're called with, or even the type of input or output arguments. Many built-in functions are polymorphic, such as the square root function, max, size, plot, and on and on. It's one of MATLAB's strongest features. But how do we make our functions polymorphic? Well, it's actually quite simple, really. The reason we waited until now to show you is that we really couldn't do it right without if statements. Now we'll combine if statements with a couple of built-in functions that we haven't mentioned yet. The first one's nargen, or nargen, which means number of arguments input. It gives the number of actual input arguments that the caller passed in. The other one's nargout, or nargout. It returns the number of actual output arguments that the caller requested. These two functions can be called from inside our functions to make our functions polymorphic. Here's the function declaration of a function called multtable with 2 output arguments and 2 input arguments. It returns an n by m multiplication table in the output argument called table. Optionally, it can also return the sum of all elements in the output argument in the variable summa. If it's called with only one input argument, it returns an n by n matrix. So let's see the code. First, we check to see whether the function was called with 1 or 2 arguments. If nargen is smaller than 2, then it was called with only a single argument. A single argument is always put in the first position, which in this case is the variable n. When m is omitted, we're supposed to return an n by n matrix, so we set m equal to n. This is a classic example of setting a default value for an input that's omitted. Now we're ready to compute the multiplication table. It's actually pretty simple. We create 2 row vectors, one going from 1 to n and the other from 1 to m. We transpose the first vector to be a column vector and use matrix multiplication to create the table. Now it's time to determine whether we need to compute the sum of the matrix as well. We need to do that only if the user requested a second output argument, so we check nargout. If it's 2, we call the sum function. Remember that sum computes the sums of the columns of a matrix and returns them in a vector? Well, that's not what we want. So here, we use the column argument to create a vector from all the elements of the table. That's done with a colon. And then we sum and give that to sum and it'll add them all up. If nargout is 1, then we avoid sum entirely. But there's no harm in computing summa, even if the caller doesn't request it. If we calculate it when the user doesn't request it, MATLAB will simply discard it when the function returns. So all we've done is save a few microseconds of calculation time here. But you will definitely want to use nargout to avoid long calculations, perhaps many minutes, when the user doesn't ask for them. In any case, here's our first polymorphic function. Let's see it in action. Well, here's our multtable function in the editor all ready to go. Let's pitch it a few different inputs to see how well it does. There we gave it 3 by 4 and it gives us a 3 by 4 array, and that looks like a multiplication table. Let's ask it for a couple of outputs. There's the table, and there's the sum. And that's the correct sum. Okay, this time we just asked for 1 output, but we only gave it 1 input argument. And you'll remember that that defaults to 5 by 5 instead of just 5. So far, so good. It's hitting them out of the park. Let's see how it handles a curveball. Well, we managed to make it fail by giving it no argument at all. MATLAB tells us the line on which the failure occurred, and we can see what happened on that line. Right here. When MATLAB tried to look up the value then, it found no value of n because we gave it no value. Well, that might seem like cheating, more like a spitball than a curveball. Let's be a little more fair. Let's give it some arguments. Well, let's do this. We got the empty matrix back. Clearly we didn't plan on negative inputs, but can you see where the empty matrix came from? Well, the colon operator here, 1 to n on line 7, became 1 to minus 3 because we gave a minus 3 for n. And the 1 colon m became 1 colon minus 5. And as we saw way back in lesson 2, when the end is less than the beginning for the colon operator, and we don't include a negative increment with it, the result's an empty matrix. Here we got 2 of them. And now we see that the product of 2 empty matrices is also an empty matrix. So now we can understand why we got the empty matrix here. And we can also understand where we got this error. But both of these cases represent traps for the user. We should do something about them.